Hello and welcome back to the Code Athlete. Today we're going for solving 3 of the 4 problems, hopefully, from Kickstart round 2021, round G. It's going to start in 50 seconds, as you can see in the countdown up here. Again, I will be working with my CodeJam template. So CodeJam and Kickstart, basically same format, both from Google. And you can find a link or 2 links in the description to my CodeJam template. The first one is a video on YouTube, which explains a bit of the features, and the second one is a link to the GitHub repo, so you can use it as well in future competitions if you want to. So yeah, usually Kickstart has 4 problems, and we have 3 hours time to solve them. I hope I will solve 1, 2, and 3, and maybe have a look at 4. But you never know. Sometimes you have difficulties with the problem, sometimes it's quite easy. Let's see how it goes. So, couldn't find the start link here, not sure. I'm registered, yes. Yes, again for problems, we start with cats and dogs. Dogs and cats, sorry. Work for an animal shelter and you're responsible for feeding the animals. You already prepared B portions of dog food and C portions of cat food. Easy enough. There are a total of n animals waiting in a line. Some dogs, some cats. It might be possible that all are dogs or all are cats. The string S of n characters says yes, C and D characters in total n. We have n animals. It's just a lineup. The animals are fed in the order they stay in the line. Each dog eats exactly 1 portion dog food, cat 1 portion. More extra portions of cat food. Every time a dog eats food, you bring m extra portions of cat food for cats. Animals have to be fed in the order they were in line, and an animal can only eat if the animal before it has already eaten. That means that if you run out of dog or cat food portions, the line will not move, as all the animals will wait patiently. You need to determine if in this scenario all the dogs in the line will be fed. Note that this means that some cats might remain in the line, but worry not, you will eventually feed them later. What is this with the extra? Every time a dog eats food, you bring m extra portions of cat food. Okay. Output, y is yes if all dogs will be fed, and no, okay, easy enough, a binary output. Let's look at the example. So 6, line up, we have 10, what was it, first dog? Yeah, 10 dog portions, 4 cat portions, and m is 0. So, but yeah, we have only 3 dogs and 3 cats, so that's enough to feed everyone. Enough. Here are no dogs. We can't feed all the cats, but we can feed all the dogs because there are none. So it's also yes. And here we have 2 dogs, but 1 cat only, and there are 2 cats in front of this dog, so we can't feed every dog. And what's with the m? So here we have only 4 dog units, and 1, 2, 3, 4. So yes, here we don't usually have enough cat food, but because when we feed the dog we get 2 more units, we can up to this point feed 4 cats. And when this dog comes, we can feed 2 more cats, so we can feed this dog, and then we can still feed 2 more cats, and we can feed this dog. And here the order is wrong, so after we feed this dog, we have 1 plus 3, 4 cat portions left, but here are 5 cats, so it's not working. Okay, so I understand the problem. How do we solve it? Can we just simulate it? It seems like we should be able to do that. Yeah, right? Because n is only 10 to the power 4. I'm not even writing anything into my notes because I think we can readily solve this. Interesting. So we have a few numbers. The first one is n, then we have d, c, and then m. And we have a string, it's a line up. It's called s in the problem. Our result type is a string, yes or no. We just iterate through the string, I guess. Let's maybe first remove all the dogs, all the cats behind the last dog, because we don't care about them anymore. So if SE is equal to cat, if C equals to 0, then we can say result equals no, and we break the loop. Else we have one cat portion less. Typo here. And in the else case we have the dog. If d equals 0, then again result is no. And we break the for loop. And in the else case we have one less dog food, but now we add m to our cat food portions. I think that should be it. Directly concatenate. Oh yeah, that was a NumPy notation. I think this should work. Yes. Let's have already a look at the second problem. With online classes in full swing, it is important for Grace to take breaks and keep herself hydrated at all times. She has decided to place a water bottle in her room in the most convenient place. This means the position should be close to all places. Desk, bed, coffee table, and more other places. Okay. The room is represented in the form of a coordinate plane. The number of steps Grace needs to go from point A to point B is equal to the Manhattan distance. Okay, interesting. Why not Euclidean? Between the 2 points, this means Grace can only walk parallel to the axis of the plane. Yeah. Can you help her find a position in the room to keep the bottle such that the sum of steps from the bottle to all her favorite furniture pieces will be minimum? All the furniture can be represented as rectangles of non-zero area in the plane with edges parallel to the axis. It is possible for furniture pieces to overlap. Really? As she likes to work on her bed table too. Interesting. interesting. Assume that Grace can simply pass through the furniture while walking and does not need to go around them. Maybe let's look at the input description. K, which represents the number of objects. K lines follow. Has 4 integers, lower and upper coordinates. Bottom left corner, upper right, top right. X and Y coordinates of the water bottle will be minimum. And if they're multiple with minimum X coordinate, and then with multiple with minimum Y coordinate. Okay. So here we have 0, 0, 1, 1. This is this piece of furniture. 2, 3, 4, 6. 2, 3, 4, 6 is this piece of furniture, and 0, 3, 5, 9 is this big rectangle. And the optimal water bottle place is here 1, 2 steps away, 1 step away, plus 0. So this is 3 spaces away from everything. I think we can regard the X and Y coordinates, because we have the Manhattan distance, independently. Yes, I think so. That should make this problem easier. So we'll start thinking about this when we see that this takes a long time, strangely. Let's take this so what is this one here? This is it, okay, yeah. So what do I mean with independent? If we look at this test case here, we sorry. So my pencil works. Yes. So if we look at the example here on the right, then and say, okay, if we look along the x-axis, and here's 0, then we have the one object which goes from 0 to 1, so it's this here. We have one object going from 2 to 4, 1, 2, 3, 4, and we have one object going from 0 to 5, 0 to 4, 5, like this. And the optimal x coordinate, now for the 0 coordinate we would have 0 for orange, 0 for red, but 1, 2 for pink. If we go here we still have 0 for those two, but 1 for pink only, so this is better. And this coordinate is again worse. It's the same actually. Orange is 0, pink is 0, and red is 1, but we always want to take the smaller x value and the smaller y value. So this is the optimal x coordinate. And now we look at the y coordinate. And again, red is from 0 to 1. Pink is from 3 to 6. 1, 2, 3, 4, 5, 6. This, and orange is from 3 to 6, 7, 8, 9. Somewhere here. I think it doesn't really matter, because again we look for the minimum. This would be 0 to red, and 1, 2, 3 to both orange and pink, so in total this would be 6. This would be in total 4. 2 plus 2 plus 0. This in total would be 1 plus 1 plus 1 would be only 3. This would be just 1, 2. So this is the best. And then from here on out it only gets bigger for red and stays the same for those two. So this is the optimal position Y. Now we have here 1 and 1, 2, 3. 1, 3 is the optimal coordinate. And we actually get directly the distances, because if we want to walk from our bottle point now to the red, which is the 0, 1 square in the lower left, then we have to walk 0 distance units along the x-axis and 2 distance units along the y-axis. So, and this is something we can directly see here. So we get from these diagrams the path, and it should make clear why we can regard those two as independent. And how do we solve one of those cases? Okay, it's I think this is can be done via binary search, because I think the distance function, if we plot along one axis, for example, here we can do this actually. We said this point has a total walking distance of 1, 2, 3 for pink and 3 for orange, so this would be 6. 1, 2, 3, 4, 5, 6. This point here has 0 for red and 2 for those, so it's 4. This point here has 1, 2, 3 distance units. This point here had just 2. This point here has 3 again. Then it increases by 1 all the time. So it's like this. Actually here again, because here we have 1 additional unit pink, so it's actually increasing by 2. And this is a convex function with one optimum value. And it will always be convex, so we can actually use binary search here to find basically the minimum. I plotted this the wrong way down, right? But the minimum is here, basically the top of the hill. And this we can do via binary search, yes. So I guess we do that. Let's have another look. So sort of feedback, I will just reload. Yeah, it's correct. Reading the input. First we had k, right? And then we had our coordinates. And we actually will split this directly into the x and the y coordinates. So actually I'm just thinking, to compute one value we need to iterate over all the objects which are k. So how big can k be? 10 to the power of 5. So the runtime of this would be of k times log of the coordinate distances, which is 10 to the power of 9, roughly 2 times 10 to the power of 9. So this value is 30 roughly. And k is 10 to the power of 5, 30 times 5. I think that should be fast enough. I think there's also a smarter solution, so I will still stick to this one. Let's make a pair x's and y's. Actually, that makes x0, x1, y0, y1. I think I like this more. And I think I got the order wrong here already. First comes y and then comes x. Okay. So like this. Oh. Or write the function which computes the distance of a point. The way to compute the distance of a point to an interval is minimum of a minus a1, a0 minus a, I think. So in case a is inside the interval a0 and a1, then this would be negative and this would be negative as well. So now we can say if this is negative, we of course don't want it, so we set it to 0 by maximum. But in case a is outside, so for example bigger than a1, then a minus a1 gives an interesting distance, and this one, because a is bigger than a1, it's also bigger than a0, so this would be negative again. Oh, what? So I guess we should take the maximum here. Yes. And are they actually ordered? Is that a condition? Yes. Good. So I think this should be fine. Actually, probably do it like this. So I have here my own lower bound function. Not documented. Oh, actually, we need. It's not a binary search, right? It's golden ratio. Oh, I don't have it implemented in the C++ template. Oh, I will need to add this. It costs a bit of time. So it's called the golden section search. Let's see if we can find a good code to copy. Let's see. It's complicated. this is Java, sorry. Really strange that I don't have it implemented. No. Sorry, I'm just reading here. Let's try convert this into C++ code. A is the lower bound, B is the upper bound. Tolerance is 0. And f is a function pointer. Which returns long form, long, and these two arrays. I think this can be done better. But I'm not too familiar actually with, like in Python I would do like a functools.partial. Basically I can substitute into this function our arrays A0 and A1 as fixed. I know there's something with lambda expressions could work here. So what is GR, the golden ratio? Let's long double, right? Like this. Always forget how to write this. Just an L also? Suffix long here, I guess so. That looks good. Let's just hard code the tolerance value to 0 here. I'm happy with that. Not sure if that works. Not sure at all. So the function is both times is compute this function, which we already wrote. Yes. The border values are just 29 here, and then we have x0 and x1. Result is actually a cell. Does that work? I'm completely unsure about this. Diddle 1085, here's the error. Was it really just that? I guess so. I think now we're stuck in the while loop. So 2, 3, 2, 2, 2, 3, 2, 2. So yeah, maybe I should print this the other way around because B is here in the end actually. So we have a line. Yes. So B gets never down to 2. Let's make a smaller equal here. Should we check maybe C minus D? Then return C. So here our binary search for, let's look at the other case. This is the binary search for the y coordinate, which is the more interesting one, I guess. So we have like here a minus 2, CD is 0, 1, and 3. Because 0 is worse than 1, we update this, so A is 0, C is 1, and D is 1. Is there a rounding function? I think the problem is here that we round down, which gives us here a 1, not a 2. Yeah. Different results, but not the one we are looking for, tragically. So 0, 3, 4, 7. 3 is better than 4, so we get 4 is the new B. 0, 4, 2, 2. Okay, let's try changing this again to A minus B. I'm just changing the tolerance value. No. Do I really have to think about this? I want to. Maybe it's 2, 4, and we have 3, 3. So it's 3, 3, 3, 4. This gives us the correct result, yes. Sorry, we need the 1 here, right? Yes. What's going wrong here? We have 0, 2, 2, 4. Maybe just let's draw this again. The top here we have here 0 distance. Here we have a 1 distance. Here we have a 1 distance. Here we have 2 distance again, so it's something like this. And before we have 0, 2, 2, and 4. Because it's the same, we update the lower one, which we don't want. In the case it's the same here, we want to update the upper. So case 2 is now correctly solved, just case 1. Both coordinates are wrong. So here we have 0, 2, 2, 4. And then it updates the upper. It's not good that C and D are the same actually in this case. No, this never stops. One and 2 is equally good. We update B to BD. Let's escape that case 2. Come on! Two, 2, 2, 3. But 3 is the correct solution in this case. Here we have 2, 3, 3, 4. Very hacky solution. I'm sorry for that. I'm not even sure if this will work for every case. I'm just hoping out for the best because it took too much time. Okay, so there are 200 point solutions already. Yes, it worked. Oh, that's very good. So this should bring us to place 400. I'm okay with that. Banana bunches. Barbara goes to Alan's banana farm when the end banana trees are organized in one long line. An array? The tree at position E, I, has BI banana bunch. Each tree has the same cost, okay? Once Barbara buys the tree, she gets all the banana bunches on that tree. Alan has a special rule. Because he does not want too many gaps in his line, he allows Barbara to buy at most 2 contiguous sections of his banana tree line. Barbara wants to buy some number of trees such that the total number of banana bunches on these purchased trees equals the capacity K of her basket. She wants to do this while spending as little money as possible. How many trees should she buy? Let's look at the example first. So, we need to understand the input. N is the first integer and K the capacity of the basket, and then next N lines contain. Next line contains N integers, yeah, just how many bananas are there. So here we have six banana trees, and she wants to have a score of 8. Cheapest is to take this one, and maybe this one. So she has to buy 3 trees. That's, I guess, the output we have to give, because there is no cost really for a tree. Minimum number of trees. Yeah. Is this 2, 3, and 3 correct? The first section can contain the trees at indices 2 and 3, and the second one, 6. Yeah. Here she wants to have 10. I mean, really, taking the 2 largest is enough. What, minus 1? Does it have to be exactly n? Oh, whoa. Equals the capacity. At most 2 contiguous, so it can also be 1 contiguous section, but it has to be exactly n bananas. Ooh, that makes it more difficult. Here we need 8. We can take 3, but then there are only 1's neighborings, so we have to take like this, which is 4, okay. 6, 3 trees. N is not too big. For most 25 cases it's 5,000, and then it's just 500. K is the basket size, which can be big, okay. I don't really have any good ideas here, first glance. I mean, the 2 contiguous sections cuts down the number of possibilities we have. We can parameterize this by 4 sorted numbers. the start of the first section, then comes the end of the first section, and then the bigger number again is the start of the second section and the end of the second section. So 4 numbers. If we have 4 arbitrary numbers between 1 and n, then we sort them, we have our 2 sections. Those are all the different possibilities, and it's that would be corresponding to n over 4 combinations, which is roughly n to the power of 4, which is too large for 500 even, I think. 500 to the power of 4 is equal to 625 times 10 to the power of 6. This would actually be just okay. So this is feasible. The problem is we have 25 cases where we have 5,000 to the power of 4, which is 625 times 10 to the power of 12. Yeah, that's too big. This is to the power of 8. Sorry, that's also okay. This is manageable in 1 second roughly, which is again too slow. If you have to do 75 test cases, I don't think we have like 75 seconds. No, it's only 20. And this second number is definitely too big, but like there might just be some minor optimization needed to cut this number down. Because if we have these 4 numbers, we can compute in constant time the sum of the 2 sections. Because if we have a CumSum array, so let's say our array is here, this 1, 2, 3, 1, 2, 3, we can compute a cumulative sum, which would be here 1, then we add the 2, so we have the 3, then we add the 3, we have 6, sorry, 7, 9, 12. And then if we have some section starting here, ending here, we can just, to compute the numbers inside, we can just take the difference, so it would be 6. So this is exclusive. If you take this, it's like this array. No, sorry, the other way around. This array. If we sum this number minus this number. So this one we can compute in statically in ON, and we can save it. It fits in memory because n is small, and then computing just one section is basically one subtraction, and then the other section is also one subtraction, and then we can check if the sum of the 2 sections is exactly k. So this works, I guess, for test set 1 and 2. Yeah, there n is small enough. Like I said, 500. Oh no, 500 actually is 1 second. This would be 100 seconds. This is already too slow for that. Are the numbers n? They are all positive, right? Because as soon as we have selected our first section, we can compute its sum, and then the other section, so if this is s, the other section needs to be k minus s, exactly. And because if we choose one starting point, we can move this here forward or backward, but this is a strictly increasing function because we always add positive numbers or 0. So actually as soon as we have this number, this position, and this position. We can search for this fourth position with binary search over all the possible solutions. This means we are cutting the algorithm down the runtime to n time to the power of 3 times. This is possibly the range of n. Usually it's smaller. So n to the power of 3 times the log of n. For 5,000, this would be 5,000 to the power of 3. Log of 5,000 is roughly 2 plus 10, 12. Not too big. But damn it, I think this is still too big actually. This is roughly 1 second, and we have here the times 12, so we have 1 second. Yeah, times 125. 100 seconds per test case. So this is still not feasible. Damn it. Of course, it's much better than 10 to the power of 12. This is more like, this is roughly, because this is roughly 10 to the power of 3, it's actually 10 to the power of 15, and this is more roughly like 2, 3, 10 to the power of 12. But it's too slow. Damn it. What can we do here? Can now definitely solve test set 2 with this approach, I think. Because if we plug in 500, we have 500 to the power of 3 times the log of 500, which is roughly 125 to the power 10 to the power 6 times 9. This is still 1 second. It's even for test case 2, it's still too slow. Oh my god. Factor 5 too slow. We need an n squared solution. It must be something like n squared times log of n. Or log squared of n or whatever. It needs to be something like n squared. So Oh, I'm really sorry, I don't have any good ideas. You probably see it all. Interesting problem, really. Because now I'm thinking if we can do anything with the k variable, which is constricted to be 1 to 10 to the power of 6. So if we have something linear in k, that would also work, but I find that very difficult to see, because why should it be linear in k? We have to, the first thing is we have to potentially split k up into 2 sections, so yeah. Also, because there are the impossible cases, I strongly suspect that we somehow have to check all possible interval configurations to make sure that there's none that can actually fulfill the sum of k. This is what I was basically trying here to do, so select one random, select the other random basically, but then I did the improvement with the binary search. I'm just thinking if you can improve another way with binary search. But I'm not really sure. I mean, I could, if we know this number s, for example, for our split, I'm sure I can say, okay, I'm looking for this binary search, but then I have to choose this value beforehand, and for this I have basically 1 to k possible values, which is even more than checking all the n positions here. So that is not a gain. That is a loss. I mean, I must say, because here I did the approximation n to the power 3 is n over 3, but basically there's a difference of a factor of 6 of 3, so actually we could divide this by 6, but still. Now this might be actually fast enough for this one. Yeah, so I guess we could, because here's a factor of 6, I guess we could solve this one in 20 seconds, 100 test cases. So I guess that's a win, that we can do test case 2. But close, so it's close to fitting into the time budget. If we implement it bad, it might even not work. What is the idea behind this? How do we get the n squared with 2 consecutive intervals? Is there something like, can we do like some pre-computation of intervals, so that if I know I have to find an interval with a... Oh, there are only n squared number of intervals. And n squared is not too large. So maybe I could do a lookup table for all the intervals that produce exactly the value k minus s. Yeah, n squared is the number of intervals. I think that is much more sensible. I will try this. So I will construct basically a map. It says sum of interval is here, and then this is basically my lookup key, and then I have here a list of intervals. Intervals basically represented by 2 numbers, start and end. And for every sum value, I might have multiple intervals. And then I can just check here, this is my, then I iterate basically over this value, this is S, and I can look up K minus S. And maybe I probably would iterate over these intervals, because here I have only n squared. Whereas if I iterate over the sum components, it's more like, I mean, many don't exist actually, because this k is bigger than n squared. Oh, actually not. For n equals 5000, it's not bigger. K is smaller. But I have to iterate then for every value here, I have to iterate over the intervals anyway. But that sounds like something now that should work. So as soon as I have my n squared selection of the first interval, I can directly look up a list of intervals that would match from the sum, and I just have to check if there's one interval which is actually not overlapping with the initial one I've chosen. And I can do this here by sorting them regarding the starting indice. I'm just trying to figure out how many combinations this is. So we have n squared for the first times I think in the worst case we have like a value s where we have roughly n squared half intervals, and then we have the value k minus s, which is also n squared minus half intervals, and then I have to check everyone with everyone. Here we're again at the n of to the power 4. It seems like no win at all. So this structure here has to be faster for a given interval here. Because of course this total number of intervals on the right side is n squared. That's why I said here n squared half, and then the rest would be all 0, of course. But still this one s value might then just cost n to the power 4. So what I need is basically, I can iterate through this one, but then I need a faster lookup. I need, from all these intervals, I need to find the smallest one, which is not colliding with the one I've currently selected. And that basically in constant or logarithmic time. So what did I say? Not colliding and smallest. Yeah. First, not colliding is a hard criterion, and then the smallest is basically the soft optimization criterion. Because we want to minimize the number of trees we buy. Is there such a data structure that can do that? I think I could cut this down to n again. By saying, I have again here, so this data structure is again basically a lookup table, so saying when the interval can start at this point, but it could also start later. What is the smallest one? Resulting in exactly this value. Then I have only n possibles. But then again we are in n cubic, which is too slow. Ugh. I don't know, actually. Actually, we could do the lookup here in logarithmic time. So that would be fast enough. I think that's the solution. So let's try that. Seems very overly complicated, but let's see. First number was n and then k, right? Yeah. I'm going to do it the wrong way around. And then we have now I want this data structure. First, let's compute cum sum. That's actually a good idea. I want the whole interval. I would specify -1. So yeah, I'm probably putting a 0 in front. That makes oftentimes things easier. Cumulative sum, very good, so we can compute fast the intervals. I make this A inclusive, B exclusive, so we return, what did I say, B exclusive. So B can be n. Yeah, I think that should, so this should be fine. What is actually the result? Yeah, it's an integer. We could directly say result equals -1, so we can return any time when we find that there's no solution. Now we want to compute our lookup, which has the following form. It's a dictionary. The first value is the sum of the interval we target for, and then for that sum we have again a lookup, where this is the starting position. And for that starting position, we get the end position, which is closest, which results in the smallest. Yeah, I think that's. Actually, let this construct in the read input again. Oh no, let's not do that. We will do this in the calculate function. Do we take the empty interval? I guess we probably should. Initialize this, and I can compute the current sum. And if this sum is bigger than the previous sum, then we can update our second interval data structure. Add the sum value, and then for a starting point, we get b. Why I'm checking that we're bigger? Because if the sum is the same, then basically we write here into the same position, in the same sum value, and the same a value. But b would be one bigger because we're going from start to finish. And that is a worse decision than taking the previous b value, because it was one smaller, and then the tree line is basically one shorter, and we pay for one less tree. If you choose that one, and it has the same sum. Of course, if we get a different sum, then we have to consider this interval maybe. So, yes. Because this for loop is n squared basically, or n squared half, we will maximum have in the second interval, counting the sum of these sizes of these second dictionaries. This will be n squared at maximum. But the good thing is this data structure is actually, so if, for example, one value, we actually have this worst case of n squared, or actually even better now, for a specific sum value, this dictionary can be at most n and not n squared, because you can see it basically here. For a fixed sum value, the second indice is the starting position of the interval a, which can only have the values from 1 to n. So even though the total of these can be n squared, one of these can never be larger than n. And now the best thing is that we can actually, are we now in n3 solution? Because now I'm thinking I need to do some post-processing to get if there's a smaller interval to the right of it for the same sum, I should delete the previous one because it's better to take that one. Yes, so the sizes of these intervals should be actually decreasing to the end, increasing to the end. Because if there would be one interval smaller behind an interval that is bigger, then it's always better to take that smaller interval, and you can always do it as the second interval, move it further to the back. So I think we need to go over all the sum values now and remove those that are bad. So we iterate over the current sum values. And then we want to iterate in a reverse manner over the intervals. How do we do that? Actually have to do iterative stuff. What did I say? The last interval needs to be the biggest. Yes. So just set this to a very large value, bigger than any interval we have. And now for the current curl size is actually bigger or even equal, because if it's equal, we can also take the value. We need to delete. Not sure how that's done. Otherwise, curl size is smaller, and we set int size to curl size. This returns an item pair, makes sense. Actually, we can set this to curl some second then. Yeah. How do we delete an element from a dictionary? Let's try and just see it. ST is first, ND is second. Again, abbreviations from my tooling, and I hope this print is now a bit cleaner. So for the zero sum, we have 0, 0, 1, 1, 2, 2, 3, 3. I guess that is fair. 1, 0, 4, 4. Ah, because it's not zero sum. Sure enough. For sum 1, we have 1, 2, 5, 6. That seems already very wrong, because we don't even have 6 values there. What is going on here? N is 4. So A can only be in the range from 0 to 3. I'm really confused about these entries. I'm not sure where they come from. Ooh, I need to clear this one, yeah. Typical. Ah. Yes, so 1 is only 1, 2, 2 is 2, 3. That's correct. 3 is 0, 1, the first entry, or 1, 3, those are 2 and some, yes. Actually, this one is larger also, so we want to keep this. So this will not be deleted. From all these here, for example, we will delete hopefully 0, 0, 1, 1, 2, 2 and only keep the 3, 3 interval. And actually, what is with 3, 4? Because it's bigger. Makes sense, but shouldn't we also have then maybe 4, 4? I guess so. Yes, we have 4, 4. I think that's better. 3 we had, 4 is not possible. Ah yes, no, 0, 2. 3 plus 1 is 4, yes. And 6 is also possible. 5 is not possible, yes, yes, yes. And after the deletion you have 0, 0, 2, 2, 4, 4. Ooh. Yes, we can only increase the iterator. We should only increase the iterator if we haven't deleted anything. Otherwise, we want to stay at the same position. Okay. Here both stay because of the sizes. That looks actually very good. We can use this, I guess, now to solve our problem. Can we check the other one as well? Maybe. So 6, 6 stays. The sum 1 is 1, 2, and 3, 4, and 5, 6. And then we keep 5, 6, yes. Sum 2 is only one possibility. Sum 3, 0, 1. 1, 3 gets bigger, 2, 4 is the same size, and 4, 5 is smaller. So we keep 4, 5 and nothing else. Yes. 4, 6, this is size 2, this is size 2, this is size 3, size 2, so the smallest one is here in the end, and we keep that. 4, 6, that's right. 3, 6, only possibility. 0, 3 is 3 size, and this is also a 3 size, so we keep 2, 5. 2, 6 is size 4, 4, 4, everything is size 4, so we keep 2, 6, 1, 6, 0, 5, 0, 6. This looks very good. This looks very, very good. I think we can use this now to actually do this n squared iteration and then a logarithmic lookup in the corresponding dictionary. So Actually, let's just first try linearly jumping through that list. Might be actually enough. For A. Can K actually be 0? No. So I guess we need a non-empty interval for the first interval. And the second intervals we have the empty interval already. The rest is smaller than 0. We can break this for loop because larger b's will always make the curse sum even bigger and the rest even smaller. And we won't find this in the dictionary, but if rest is not second interval, in this case we just continue because smaller b values might make curse sum larger and the rest smaller, and smaller values might again be in the same interval. Now we actually have our dictionary lookup. Actually, we can say here if result bigger than 0 and smaller than b minus a, and also break, because b minus a is the size of the first interval. If that's already too big, we can take a shortcut here. Start for each start end in second interval rest if start end first bigger or equal to b, then this is a valid interval, and it's because we sorted them and they're always getting bigger to the end. This is the smallest one we can't find in the first one. So we can directly take this minimum of the previous result, or b minus a plus the new interval we just found, and then we can break this for loop. And we get the wrong results again. We produce a lot of minus ones. Yes, because the minimums case of course doesn't work. That's the correct solution. Let's check if it's fast enough. I don't think actually, but I want to have a look at the fourth problem. And we can speed it up afterwards, because I think we should be able to do a binary search over this condition here at this point. Because this is now an n squared, and this should be log n and then it's fast. Yes. Did we actually compute that? What is this for 5,000? 5,000 squared times log 5,000. It's roughly 25 10 to the power of 6 times 12. $250, 300. So this is 3, 10. This is still pretty slow. Wow. 25 of these cases. I'm sure if this is even fast enough now. So this probably won't work at all from the third test case. So we have 25 test cases of those, which is 7.5. 7.5, 10 to the power of 9. So this is, okay, this is 7 seconds for those 25, and then we have still 12 seconds. I will directly check this. Yes, this might take 20 seconds. So, small text, that's good. You're given two integers, the number of vertices in an area. You need to construct a simple polygon of n vertices such that the area of the polygon is exactly a half. And all the vertices have non-negative coordinates with value up to 10 to the power 9. A simple polygon is one that defines a closed area, does not have self-intersections, even at a single point. No two consecutive edges form a straight angle. Otherwise it would not really be a vertex here, I guess. Yes. First line of each test case contains two integers, n denoting the number of vertices and a denoting double the required area of the polygon. Why is it possible? It's not possible. Impossible otherwise. So just a binary answer again. If you output possible, no. Output n more lines with two integers each. Line should contain two integers x, y, and y, which denote the coordinates of each vertex for each y. The coordinates should satisfy this condition. So it's inside our big rectangle. Should be in consecutive order. Yeah, if there are multiple possible solutions, you can output any of them. Ooh, oops. I hope you can still see this well. So 4 is 4 vertices and 36 should be the area. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the area of it repeats. Don't know how this is called in English actually. This should be then 8 plus 4 is 12 times the height 3, 36, and then half. So yeah, we get it exactly 36 half. This shape, and 5 points, the area of 2 is impossible. Interesting. I'll zoom this back now. This is, by the way, GeoGebra. I recognize this directly, the points, and so geogebra.com is a nice online graphics tool to do some geometry. And actually, what here should be helpful is a theorem of peak. Not sure how it's written. Peak. Sorry, this is German. Let's speak English. Yes, because here we look also at polygons with integer coordinates for all its vertices let I be the number of integer points that are interior to the polygon, and let B be the number of integer points on its boundary, including vertices as well as points along the sides of it. Then the area A of this polygon is integer plus boundary half minus 1. So we can use this directly, I guess. We can directly see why 5 is not possible. It's very nice. Area is equal to interior plus boundary half minus 1. Let's multiply by 2 because we have actually our A is double the area. So the A from this is actually our A half. And now we can double this equation. So now we have the A from our problem statement, 2I plus B minus 2. And boundary points are also vertices, yes. So if we plug this in, if we want to have 5 points, that means B is bigger than 5. Interior we could possibly get to 0 maybe. So the area is always greater or equal to B minus 2. Not the area, the double area, but that means that if you have B equals to 5, A has to be at least as big as 3, that's why 2 is not possible. Nice, right? So now the question remains, and I guess the other way around, if this condition is fulfilled, we possibly can construct a polygon with I equals to 0, because if you look at this grid, for example, you can always make them very, very, very steep, these lines, and then go maybe back to some point over here. No, actually now we have points inside. But if we don't go 2 levels lower, but only 1 level lower. Now if we... Oh. Now I'm not too sure anymore. I would say that's possible. So maybe there's a complex condition between B and I. So a certain number of vertices. For example, let's say we have actually 5 vertices. Can we construct an area of 3? Or 1/2 better said. Can do this. I guess this would work. There are no interior points. This left half has actually an area of exactly 1, and this right half has 1 times height of 1, and because triangle formula, this 1/2. So this is actually a valid solution for A equals 3. Can I generalize this construction given some B points that we can always like given a B and a A, we can calculate the number of points I. And so I have been given I and a B, and now I just have to fulfill these 2 conditions basically. How do I construct it? I'm not sure if it's easy to always get B equals to 0. So let's maybe try B equals to 7. Can I construct something with B 7 and I 0? I like to start. How many points are I have already some. Oh, can I always do something like, what is with e equals to 6? I'm just thinking I could always walk like this and stop somewhere. And then connect it here on top, like this. And for every, this is interesting, for every interior point in the end, I can just here go, like if I want to have two interior points, I can just walk two by side, and I have here my interior point and here my interior point, and connect this over. So I think this is a nice starting construction, just looking at the parity now, because these zigzag curves start here. If I have to get up, it's 3 more. And then what I'm trying to say is I could do like this. Ooh. And now I can't connect to the top. There are like special cases. Yeah. Let's maybe walk this zigzag line. Is that better? Oh, no, it's not. And this is not allowed because of these. They count as boundary points. Oh, but I can do this. And with this construction, I can include as many interior points as I want. I like that. Okay, so we have one part that is constructing the interior points. So let's say I is bigger than, or at least one or bigger. We can do something like this. So here we have 2 interior points. And we have already 4 vertices. So this is only for b bigger or equal to 5, I guess. Plus 5 we can do like this. 6. We can do like this. Right? So we can do like this. Maybe we can do like this. If I need to add +3, I need these two and this one. So I can always go down and up. And if I need an even number, I need to stop here, but get also this one down here. So I need to like this, start downwards. So that is something I can generalize. And I just have to implement the small numbers, I guess, with I equals to 0 or b smaller than 5. B always has to be bigger than 3, right? I will start with this, even though I haven't looked at my banana bunches, which should be through by now. Yeah, as expected. We will come to this later, so I'm not quite sure if I even have a good solution for that. Still 1 hour. We could maybe finish all problems actually. I would be very happy with that, but let's don't celebrate too early. We just get the input DNA. Could actually copy this task. I will call it B because we now have this nice formula. We need the default value mode, and if the result dot size is 0, then we don't have a solution. Otherwise, list of cells. Yes. Let's clear the result. If 2i is a plus 2 minus b, if that is not divisible by 2, there is no solution for I, so we can just return immediately. Otherwise, you can say I is equal to a plus 2 minus b divided by 2. And if this I is now negative, you can also directly return, because the negative number of interior points is not possible. And now everything else is constructible. And we need to handle these small edge cases. B equals 3 and B equals 4. And I think in the special case I equals 0 is also somewhere in there. So if B equals 3, small triangle. n is smaller than 1000, so we never run out of space. That is good. No, sorry, triangle. We just need 3 points. I is 1. Yeah, this is 2, 1. That's correct. And we can return this case. If b equals 4, then again if I equals to 0, this is the simple square we have here. 1, 1, 1. They need to be in the correct order. That's why I need to watch out here. Else, yes, we can result of pushback 0, 1, 1, 0. Five plus 1, 1, I would say. And 1, 2. Yeah, that should be a 4-point thing that would solve this. And in the end, now we take our general construction. We need the x offset to be let's make it big enough, b. Because we will have here to the left, we will have roughly b half points, and these are always 4 points to the right or so. So if we shift this all to the right by b, then we have enough space to the left to make this long enough. And to the right we do this again, this triangle construction where we have enough inside points. So we will, I think I will start with this point here, go to the right, down here, and then I need to calculate this shape we draw here. So the first one is result x offset, we said we take b, and then we are 2 in the y direction. The number of inside points is again this triangle part, and we go back to b, and then we go the small step up. Now we have our interior points, and now we need to do the zigzag curve. So rest b is equal to b minus 4. y rest b bigger or equal to 3. We can say x offset, make it one smaller, result of pushback. Actually, I haven't used x offset here, but b all the time, which is a bit irritating for me. X offset now the order really doesn't matter. 0 offset 1 and then rest b, this we decrease by 2 because we already have 2 again worked out. So if it's now 3, let's make this order equal to 2. Yes. Now rest b is either 0 or 1. If rest b equals 0, return. Otherwise rest b is equal to 1. We have one more point, we go 1 to the left. I think this should be it. Can copy those, but of course our solution will construct different things. Okay, one sad thing is our solution actually produces a solution for the case 2, which we know is impossible. We have to check that one first, and we also have to fix the formatting. So what is this function here? Oh, and I need to print an impossible beforehand. So we fixed the formatting first and foremost. And I think this might be correct. Actually, let's start up GeoGebra because I talked of it already. So you can directly see how it works. So we have 0, 1, which is this point. Then we have, actually directly draw Polygon. Then we have 1, 0, which is this point. Then we have 18. One. this point. Then we have 1, 2, this point. What is the area of this? 18, which is exactly half of 36. Yeah, should be. So that solution is correct. Let's check solution 2. Why does it print something when it's impossible? Actually, first of all, let's copy this solution to result. 0, 1, 1, 0, 81, 1, 2. Yes, and now case 2. A plus 2 minus b is minus 1. So this check doesn't work. So if it's smaller than 0 now, I will handle that explicitly. And I think this should be correct. It was a forced solve for a fourth problem. Can go to the banana bunches again. Shall we try to do the binary search there? What? Wrong answer. That is really bad. Is there another restriction in this? That is definitely satisfied because n is just not big enough. Oh, but the area is. Oh, we can check this actually. One test case, reading input, 2 numbers. The first one is n, let's set it to 1000. The second one is a. Yeah, I guess that is the problem, right? No, wait. Oh, this is half of it. This is not the problem. And I mean, the formula must be correct. It's the theorem of P can be correctly took it from there. We just have to check if all these cases are correct, I guess. I will do this first because it gives us more points. So B equals 3. Let's set it to 3, and then the area must be 1. What? One produces this, yes. So let's check that for a moment. 0, 0, 0, 1, 1, 0, 0. And we have an area of 0.5, which is half of 1. That's correct. The second case is with some large E. So again, we have equal to 3 and some large odd number. Okay. We start with 0, 0, 1, 2, 51, 1. Note, this is too silly. 3 and 1, 2, and 6, 1. 5.5 is half of 11, and we have 3 real vertices. So with increasing I, the seed just wanders to the right. It gives the correct area. So these two cases are indeed correct. Let's look at these two. We have 4 points, and with I equal to 0, this area should be 2. And this should be very clear. This is 0, 0, 0, 1. 1, 1, 1, 1, 0. And the area is, it's 1. Sure. And we specified A equals 2, so this also fits because we always specified the double area. Again, 4 points with a larger I. This one needs to be even, so let's make it then 12 in this case. And we have 0, 1, this point here, 1, 0, this point here, 6, 1, this point here, 1, 2, this point here. Area of 6, which is 12, fits the bill. And also a true polygon. And now we need to check this case, and I guess here's not really an if clause except for this one here. So this is different for, I mean, let's check this with b equals to 5 and I equals to 0 means area of 3. We have 5, 2, 6, 1, 5, 0, 5, 1, 4, 1. What was this? 5 points. Area is 1.5, which is half of 3, which is correct. Next one would be 5 and not 3, but maybe, yeah, 5. Only a slight modification. 5, 2, and instead of 6, it's 7, 1. 5, 0, 5, 1, 4, 1. So you can see here's this offset of 5, because you need to put all those points there. And again, we have an area of 2.5, which is half of 5. Everything's fine. So this could be increased. This is fine. Let's check 6 and 4. Start at 6, 2, 7, 1, 6, 0, 6, 1, 5, 0, 5, 1, and 6, 2 again. 6 points. Area is 2. And we specified 4. So that's correct. It's also a true shape again. It's 6, 4, let's make 6, 6. 6, 2, 8, 1, 6, 0, 6, 1, 5, 0, 5, 1. Finished. Area of 3. Fits the bill. Six, 5 should not be possible. Okay, yes. Just to make that check. 7, 5. I'm not sure right now where the bug is. I'm doing very explorative search here. 7, 2, 8, 1, 7, 0, 7, 1. 6, 0, 6, 1, 5, 1. This is all fine. And again, this should be an area of, what did we say? 5? Yeah, 0.5 is correct. And we'll always do the zigzag and always end up in the top of these two. So if it's even, we do need to do even points here. We'll go like this and this. We've seen this previous. And if it's odd, it will go like this. This is basically the 2 lines down here. Making sure we always stop at the 1 coordinate in y direction, not at 0. Because if we would go like down, we couldn't go back to the A. But from all those points here, we always can connect back to the starting point. And because this is in total B points, we should never go to -1 here, because they're all 1 apart just here. Should always be space enough here. All is in between 0, 1, and 2. And yeah, the maximum coordinate here is basically, we can see this here, x offset plus y plus 1. X offset is b, and I is a plus 2 minus b half. If I add b there, basically a plus 2 plus b half. But yes, a maximum of a is 10 to the power of 9, and a half, a plus b is then just 10 to the power of 9 plus some small amount divided by half is half the size of this, so we are always good. I'm just seeing here, we failed the small test case, which is only 3 to 5 points. How did we manage to do that? Damn it. I was very hopeful when I saw this problem, and now it seems I have a bug and I can't find... what is a simple polygon? Maybe it has to be convex. No, it doesn't have to. That's not it. Just to make clear, our construction is always that we don't have any points on the sides here. So here it's clear that we don't have points because how should that be? But if this b wanders out, this line will always be between the 0 and 1 y coordinate, so it can't intersect with any other integer position here. Same goes for this line, and the same goes for this line. So we really only have these integer inside points, so the area should always match. I mean, we saw this here. 3 to 5, this is really making me curious now. There is something in the problem saying you're given two integers. Any vertices area, you need to construct a simple polygon. It's exactly a half, and all the vertices have non-negative integer coordinates. This is fine, I've checked this even. Let's check it again. B is 5 and A is 2, 4, 5, 6, 7, 8, 9. So that's possible. So it's 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. This should be possible. Yeah, it's smaller than 10 to the power of 9. And it finds a closed area, and that does not have self-intersections, even at a single point. And that no two consecutive edges form a straight angle. Oh, this is a straight angle, not 90 degrees. Is it 90 degrees? Yeah. What? There's something is right. Which equals to right. equals 2 right angles. Oh, okay. No, our points are not aligned. We saw this shape here, it was a simple triangle. We saw this shape here, was also quite a simple triangle. I think this would have not I equals to 0. Would this have worked for I equal to 0? That would have been 0, 1 is here, 1, 0 is here, 1, 1 is here, 1, 2 is here. No, it would not have worked. For b equals 4, I can't be 0, right? Oh yes, if 2, a is 2. I is definitely positive. I am super confused by this now. And we solved the sample, so our sample output was correct for that one. What is wrong here? Think about writing my program to check my output, but is the printing broken for multiple test cases? Maybe we can check that actually. Comparison. No, it's fine. Curious to know which test cases here fails. Which is a funny end. That's definitely. Clear the result. Sorry, I just realized what my problem is here. So this condition is correct, but I can of course add more boundary points, which, oh, stupid me! I call this the edge point. We set it to 0. Or we actually set it to this value. So if this one, we need one edge point. In Peake's formula, edge and boundary is basically the same. If it's a corner or on the edge of something, but with this we can always have I value. Ooh, and now we have a terrible, much more terrible, more test cases. Damn it! Ah. Yes, the impossible case, we got them wrong. Damn it. How do I fix this? I mean, I found out that this is basically this, so this solves also the I equals 0. So I will try to simplify this and delete this here. But now I can actually do it like this, because if we need an edge point, then we get here to 0, 2 and have the 0, 1 edge point basically. So this should work. Now for the square, in this case we can also just, if we need an edge point, push this one out here. And in this case, 0, 1, 1, 0. This construction is a bit trickier. Our polygon is constructed something like this. Here we get the I interior points. And now can I select this point? I selected it like this, so we don't have any edge points. Can I do something different here? I have 2 edge points. Oh, I guess I could move. So I could offset this top point to here and then go here. Then I have here an edge point. So this top point is at 1, 2. This needs to go to 0, 2 if we need an edge point. And the starting point was at 0, 1, which needs to go to 0, 0 if we need an edge point. And now this case here, where do we put an edge point there? I could move this. Could move this G in this construction one more to the left, and then we have here an edge point. But in the case we have, for example, 6 points, we would construct 1, 2, 3, 4, 5, 6. And connect it back. So if our last edge is not this one, but like going up, because we have here an even number we need to put, then let's just draw that to think better about it. So here we have our E interior points. What is something like this? Move it into here. I guess so. We could reduce the offset here by an edge point. But then we need to start here with 1, 0. And we need to stop at 3. Zero. So we go 1, 0. Have here our elementary edge point. And now RESP is either 2 or 1. If it's 2, we go like this. If it's 1, go directly up. Just this case here. I'll try this directly. So much faith. Not really. This is really hacky. So again, let's test this. Let's actually put some more test cases in here. So I basically know now that every area works. 5, 3 should work. 5, 4 should work. Small test case is done. Nice. Why is the big test case not wrong? What? Okay, so let's check maybe bigger points than 6, 4, 6, 5, 6, 6, 6, 7, 7, 5, 7, 6, 7, 7, 7, 8. How many lines do we have? 12. So let's look at test case 12, the 7-8 thing. You have 7-2, 9-1, 7-0, 7-1, 5-1, 5-0, 4-1. Area is 4, which is correct. And we have 7 points. 1, 2, 3, 4, 5, 6, 7. Also correct. Looks good to me. The one on top, 7-2 again, 9-1 again, 7-0, 7-1, 6-1, 0, 5-1. Finished. 7 points again. Area's 3.5, which is correct. Seven 2, 8-1, 7-0, 7-1, 5-1, 7-1, 5-1, 5-0, 4-1. Again 7 points. Area's 3, which is correct. Test case 9. 7-2, 8-1. 7-0, 7-1, 6-1, 6-0, 5-1. 7 points again. Area is 2.5. Just what we wanted. 6-point configurations. Test case 8. The 5 points we don't have to check anymore. So, test case 8, 6-2, 8-1, 6-0, 6-1, 4-0, 6-1, 4-0, what? 4-1, 4-1? Yeah, that is wrong. Let's stop there. The 6-7 test case comes here with a 2, so we are in the rest b equal to 2 test case. Oh yeah. That doesn't work, does it? What do we do in this case? I can draw 2 points. Go like this. Maybe this on top is a better generalization actually. We put here the E. Yes, I like that very much. Much better. 7 minutes left. So let's get directly into checking our outputs again. For the 6er case, let's start directly there. So 4-2, 6-2. Oh yeah, start differently. 4-2, 6-2, 8-1, 6-0, 6-1, 5-1. 6 points. Area 3.5, which is correct. And the one above moves just this point here. Looks good. And then the one above that, it's again 4-2. 6-2, 7-1, 6-0, 6-1, 5-1, 2.5. Yeah, that's correct. The one above that makes this to a 5-2 again, which is 4, which is also correct. And we have the complete solution. Nice. Now I'm pretty sure I won't make this in 5 minutes fast enough to solve this. Actually, if it's really just doing a binary search here. Is there like a function built-in which I could use? Find something like lower bound? Yes, lower bound. So it's an iterator pointing to the first element that is not less than. We need a greater or equal, so this is actually okay, not less than b. I think it points to the end. Not equal. Then we have this. This is a pointer now. Still the correct solution. Would be crazy if this is fast enough. I would be very happy about a full score on this round. Is it actually normal that that everything is visible? Start? I don't know. This was definitely my last try. Currently we are in a very good place. Very happy with that already. This would be, of course, the cherry on top. Getting 100 points here. Quite a few that managed that to do actually. Oh yeah, from the one that actually wouldn't really be a big jump actually. Oh well, maybe 329. Don't have that much penalties. So, let's recap. I hope you enjoyed watching me solve these problems. I think I didn't do too bad. This one, after only 8 minutes, was okay. It was easy. I maybe should have gotten it a little bit faster actually. Let's have a look at the solution. I did this ugly removing of the cats. But then, yeah, it was just simulating, so nothing too fancy really. I mean, I read the tasks quite slowly, so it always counts to the time. This was okay-ish. I mean, half an hour for figuring this out. Yeah, the golden section search. I really need to put this into my template. So I will first of all push, of course, my solutions, and maybe a few days later I will actually implement this correctly. I actually had it in my Python template, so maybe I should have switched at that point when I realized this to my Python template. Also, I get always confused between binary search and golden section search. Those two are actually two different things. The golden section search looks for a minimum in a convex function, basically, or a maximum in a concave one. And the binary search looks for a specific value in a monotone, the increasing or decreasing sequence. So yeah, really two different things actually, and I struggled quite a bit with this one here, tweaking the parameters, so that's why I need a good documented baseline function for C++ here. That was ugly, this part, sadly. Yes. Also here, this giving these two just as parameters, usually you would, I think you would do actually at this point a lambda, C++ lambda expression, where you capture already these two arrays x0 and x1 as part of the function call, which I think you can do. I will look this up to have it ready in my brain for next time when I use this, but probably this will be so far in the future that I have forgotten it again. Yes. But yeah, decoupling x and y coordinates and solving this with the golden section search was okay, I think. There's probably something better you can do actually. Let's have a short look. Oh, we could have directly gone over the points of k. Yes, sorry. How large was k? Yeah, so that's what would have been. Yes, because if you take an edge and you have on the left more rectangles than on the right, then going to the right, from my perspective, sorry, would put here always more distance on this side than on this side, so the optimum would be here. But if you select another where more rectangles are on the right than on the left, then going that way would be worse. So that's why actually the optimal points always lie on the, you can actually see this here quite well. The optimal point has to lie on an edge of one of the containers, which in this case is a red one, and in this case it's a pink and orange one at the same time. So yeah, that was. Then you just need to iterate over 2k points, and 2k is 2 times 10 to the power 5, which is fast enough. You don't need the golden section search. But I think the golden section search is actually faster, because if you take the logarithm of this, this is basically the area I looked in, and it's basically logarithmic. Not sure what the exact factor is, but roughly logarithmic over this interval. Then you would get yeah, let's calculate this logarithm. The base of 2 of 4, 9, 31 iterations only. So yeah, roughly that, maybe 60 or 100 of course, but much faster than 2k, definitely. Interesting. Banana bunches. Still haven't got a judgment on this one. No, still too slow. I suspected this. In the end, I was a bit surprised when actually I thought this one would be definitely fast enough. But when I plugged here the 5000 in, I got for 25 test cases, which were given this size, a very optimistic estimation of 7.5 times 10 to the power of 9 operations, floating point operations. But like, this is not realistic in the end. And roughly, well, this is realistic, but roughly, I count roughly 1 second for 10 to the power of 9, so this is 7.5 seconds just for these 25 test cases, and the other 75 should be with 500 here, so they should actually be quite a bit faster, 100 times faster, I guess. I guess we were quite close with this one, but I suspect now that there's a solution running in ON. Oh, ON squared. I mean, that can make all the difference. I mean, okay, n squared, but then I need to do something constant here, which I didn't manage to do. I had this logarithmic lookup, which is not optimal at all. And this log factor is really this factor of 12. So power of 10. And I said like this might have been very close to the 20 seconds, power factor of 10, and you have algorithm which runs in 2 seconds and has no problem at all. Damn it. That was a really close one, I think. Yeah, the simple Polygon, I was very happy that I knew about peak. Probably the first statement I do here, yes, according to Peak's theorem, yes. Oh, but they have much nicer shapes actually. Yes. Where do they have the inside points? Oh, actually, you know what? Why take inside points at all? I did it much too complicated. I could have put all in the edge points. Yes, this is totally smart. Of course, then you have to watch out that you don't run into this 10 to the power of 9 problem, because the number of edge points now scales linearly, not with a factor of 2, but with a factor of 1 with the area. This number could be 10 to the power of 9. And then the number of edge points you would need, it could also be of the size 10 to the power of 9. And then you might run into these boundary issues, which I had no problem with at all, but now I had stupid many test cases. So, yeah, that was Kickstart Round G 2021. I hope you had fun solving maybe some of the problems also yourself, and now looking at my solutions, gloating over me when I've done a really bad case of the simple polygons, which were too simple for me now, and too simple in the sense that I made it much too complex than it really was. Yeah. And the bananas. I have to look at that analysis to find out what's going on. Golden section search not implemented in my template. Oi oi oi. If you like this video, feel free to check out my other videos. I did in the beginning of this year the Code Jam competition, a few rounds, and recorded them. Have a look at those. The past few days I also recorded a few solutions from Kickstart Round G. If you find those interesting, also have a look at those. Otherwise, again, the link to my solution, which will be uploaded to GitHub, is in the description. The link to my GitHub code template as well. And I hope to see you soon. Please ring the notification bell so you'll really see me. And maybe leave a like and a subscription. It really made me happy. Thank you. Bye.